Bismillahirrahmanirrahim. I am Dr. Asad ullah, lecturer, Institute of Numerical Sciences, Guwahati University of Science and Technology. Dear students, welcome to the course of Calculus 2, course code MATH-102, lecture number 8. In this lecture, we will discuss limit of functions. In this lecture, we will try to cover the following points: definition of limit. Number 2, limit of constant and identity functions. Number 3, functions that have no limit in their domain. So I will provide some examples and also explain it graphically that how inside in the domain of functions we cannot find the limit or we don't have a limit. Number 4, I will explain the laws of limit with examples. And number 5, I will provide some practice problems to the students. And finally, there will be references. Limit of a function. Let f of x be defined on an open interval about x naught, except possibly at x naught itself. If f of x gets arbitrarily close to L, as close to L as we like, for all x sufficiently close to the point x naught, we say that f approaches the limit L as x approaches x naught. And mathematically we write limit x tends to x naught f of x is equal to L. We say that the limit of a function as x approaches x naught is L. Essentially, the definition says that the value of f of x are close to the limit L whenever x is close to x naught on either side of x naught. In this definition, here it is written that except possibly at x naught. What does term mean? In limits, it is not necessarily that the function is defined at the point at which we are finding the limit. So in later we will discuss this in detail, that how it is possible that we can find the limit at the point where the function is not defined. Here we present a simple example in which the behavior of the function f of x is equal to x square minus 1 divided by x minus 1 is to be analyzed at the point x is equal to 1. Now here if we use x is equal to 1 directly in the function, we get 0 by 0 form, which is an indeterminate form. So the function is undefined at the point x is equal to 1. Now we can find the limit by factorizing x square minus 1 into two linear factors, x minus 1 into x plus 1. Now cancelling x minus 1 with x minus 1, we get f of x is equal to x plus 1 for x not equal to 1. We can use this factorization and this cancellation actually when x not equal to 1. Otherwise, this simplification is not possible. Okay. The limit of the function f of x is equal to x plus 1. If we use x is equal to 1, now we get f of 1 is equal to 2. So the limit of the function f of x is equal to 2. But since this limit is the function of x square minus 1 divided by x minus 1, because we have simplified x square minus 1 divided by x minus 1 to get x plus 1. So the limit 2 represent the limit of the original function limit x tends to 1, that is x square minus 1 divided by x minus 1. So in this example, the function is not defined at x is equal to 1, but still we have a limit that is equal to 2. Table 2.2 shows the numerical behavior of the function f of x is equal to x square minus 1 divided by x minus 1 at the point x is equal to 1. In the previous example, we have shown that the limit of this function is equal to 2. Now we choose some points on the right side of the point x is equal to 1 and check the behavior of the function, and then also choose some points on the left side of this point and check the behavior of the function. On the left side of the function at the point x is equal to 1, the function value is 1.9, that is at 0.9 we get 1.9. And if we increase this value that is 0.99, 0.999 and up to this point, we get the function value is near or equal to 2. And similarly on the right side, 1.1, the function value is 2.1. And if we decrease this value up to this point, the function values goes towards the point 2. So on both sides of the point x is equal to 1, the function value goes towards the point 2. Now here are two graphs, that is the graph of f of x is equal to x square minus 1 divided by x minus 1 and the graph of f of x is equal to x plus 1. This is the original function graph, this one. And at the point x is equal to 1, here is a hole in this graph. This shows that the function is not defined at this point. As we have checked in the previous example, when we use x is equal to 1, we get 0 by 0 form. That's why the function is not defined here. Now, after simplification and factorizing x square minus 1 into x plus 1 into x minus 1, we get the function value f of x is equal to x plus 1. Now, at x is equal to 1, we get the function value 2. So now, this hole is filled now. So the function value is at this point equal to 2. Here we present three different examples, f of x, g of x and h of x, and we are to show here that the function value and the limiting value of the function is not necessarily equal. Now we are to find the limit at x is equal to 1. So in the function f of x is equal to x square minus 1 divided by x minus 1, the function is not defined at this point, but still we have the limit equal to 2 as we have proved in the previous example. In this piecewise defined function, the function value as x tends to 1 tends to 2. So the limiting value of this function is equal to 2. But the function value at the point x is equal to 1 is equal to 1 because the function is defined here. So in this case, the function is defined at the point x is equal to 1, which is equal to 1. But the limiting value is equal to 2. So the limiting value and the function value is not the same in this case. In this example, h of x is equal to x plus 1. The limiting value and the function value is the same, that is at x is equal to 1, we get 2. So the limiting value is also equal to 2 and the function value is also equal to 2. So the limiting value and the function value is the same in this example, h of x is equal to x plus 1. Now, this is the only example in these three examples in which the function value and the limiting value is the same. Techniques for evaluating limits. The previous two examples are just the clarification of the definition of the limit. Now, to go ahead for the evaluation of more complex limits, we use different techniques, that is the direct substitution, and beside this we get some different forms of limits, that is 0 by 0, infinity by infinity, infinity minus infinity, and so on. These are all indeterminate forms. We will later discuss these forms in detail, but here we will go to the direct substitution property. The direct substitution property. If f of x is a polynomial or a rational function and a point a in the domain of f of x, then limit x tends to a of the function f of x is equal to f of a. This means that if we have a polynomial or a rational function and if we are to find the limit at the point a that is inside in the domain, so we have just to use this point in the function to evaluate the limit. Okay, to explain the direct substitution property, I am presenting an example. Here we choose different polynomials, that is in the first case, that is f of x is equal to 4, which is a constant function. So later we will discuss that what is the limit of the constant function by using a theorem. So here when x tends to 2, the constant value is again the constant value. So the limit of the constant is a constant. Similarly, in part B, when x tends to minus 13, again the limit of the constant 4 is equal to 4. In part C, when x tends to 3, the identity function x limit is equal to 3. So we can use direct this point x is equal to 3 and we get the function value equal to 3. So that is using the direct substitution property, we get the limiting value equal to 3. Now here again we have a polynomial 5x minus 3. Using x is equal to 2 directly, 5 times 2 we get 10, or 10 minus 3 is equal to 7. So this is the limit of part D. In part E, the limit x tends to minus 2, that is a rational function 3x plus 4 divided by x plus 5, which is defined at x is equal to minus 2. So using the direct substitution property, using this x is equal to minus 2 and this rational function, we get minus 2 by 3. Now what will be the limit of identity function and the constant function? I am explaining this by using example number 8. So in part A, we have a function f of x is equal to x. This is an identity function, and we are to find the limit of this function at the point x naught. Okay, limit x tends to x naught, f of x is equal to limit x tends to x naught of the function value, that is f of x is equal to x, and using this x naught in the function, using the direct substitution property, we get x naught. This is the limit of the identity function. So the limit of the identity function is x naught as x tends to x naught. Now in part B, the constant function f of x is equal to k is chosen, and again we are to check the limit of this constant function at the point x is equal to x naught. So limit x tends to x naught, f of x, that is the function value, this is equal to k. So k is constant, so as we go towards the point x naught, the function value, that is k, remains the same. So there is no variable inside k or in multiplication with k, so k will remains the same. So the limiting value of the constant function is against the constant k. Now in example number 9, I have chosen three different functions, u of x, g of x, and f of x. All these three functions are piecewise defined functions. Now a function may fail to have a limit at a point in its domain. It means that inside in the domain of these three functions, we cannot find the limit of the functions. Now all the three functions are plotted here, that is the unit step function is plotted in graph A, and g of x is plotted in graph B, and f of x is plotted in graph C. Now since we are interested to find the limit at the point x is equal to 0 in all the three cases, in the first case, that is the unit step function u of x, if we goes towards the point 0 from the left side, the function value also goes towards 0. And similarly, if we go towards the point 0 from the right side, the function value goes towards the point 1. So the limiting value from the left side of the function is equal to 0, and if we go towards the point 0 from the right side, the function value is equal to 1. So the function value at the point x is equal to 1 is not unique. From the left side we get x is equal, f of x is equal to 0, and from the right side we get the function value 1. So the limiting value on the left side and on the right side is not unique. So the limit does not exist at the point x is equal to 0. Now in part B, again we are interested to find the limit at the point x is equal to 0. If we go towards the point 0 from the left side, the function value also go towards the minus infinity. And similarly, if we are approaching towards the point 0 from the right side, the function value goes to a positive infinity. So from the left side we get negative infinity, and from the right side we get positive infinity. So the limit is not unique, and so the limit does not exist at the point x is equal to 0. In this example, I am approaching towards the point 0 from the left side. the function value goes towards 0. And if I am approaching towards the point x is equal to 0, from the right side, the function value is not unique in 1 and minus 1, because here is an oscillation between minus 1 and plus 1. So that's why due to these oscillation, the function value is not unique. So from the left side, I am getting the limiting value 0, and from the right side, I am not getting a unique value. So the function is not the limiting value is not defined on the right side, because we have no unique limit in 1 and minus 1. So the left and right limit are not unique, and thus the limit does not exist at the point x is equal to 0. All these 3 points, that is x is equal to 0, here also x is equal to 0, and also x is equal to 0 in this graph, inside in the domain of their respective graphs. Laws of limit. I am explaining these laws by using a simple theorem. If we have two different functions, f of x and g of x, and if you are interested to find the limit of these two functions at the point x is equal to c, that is, the limiting value of the function f of x at this point is L, and also the limit of this function g of x at this point is equal to m, then we have rule number 1, sum rule. If these two functions are in addition, f of x plus g of x, and we apply the limit x tends to c, we can find their limits separately. That is the limit of f of x plus the limit of g of x at that point x is equal to c, which is equal to L plus m. Similarly, in difference rule, we can apply the limit f of x minus g of x, that is limit x tends to c, the limit of the function f of x minus the limit of the function g of x, which is further is equal to L minus m. Now in product rule, these two functions are in multiplication. What we will do in this case, we are to find the limit these two functions separately, that is limit x tends to c f of x multiply by limit x tends to c of the function g of x, which is equal to L multiply by m. Constant multiple rule. If we have a function which is multiple of k, then we can find the limit of the function f of x and just multiply this limit by a constant k. It means we can common out the constant k from the limit and applying the limit on the function f of x, which is equal to L in this case. So we get k times L. Rule number 5, quotient rule. We have a function f of x divided by g of x, and we are finding the limit at the point x is equal to c. So which is further is equal to L divided by m, provided that m not equal to 0. From this property, the limit of a constant of two functions is the quotient of their limits, provided that the denominator is not equal to 0. In property number 6, which is also called power rule, here we have a function f of x power r divided by s, and we are interested to find the limit at the point x is equal to c, which is equal to L power r by s. So this is the limit of the required function, but it must be a real number. If it is not a real number, then this is not the limit of this function f of x power r divided by s. Okay, to understand the laws of limit, here we present three different parts in example number 1. To evaluate part 1 at the general point x is equal to c, we use laws of the limit, that is sum and difference rule. So applying the limits separately, we get limit x tends to c of the x cube plus limit x tends to c of the 4x square and limit x tends to c of the constant 3. So the limit of the constant is always equal to a constant, so this is equal to 3. And here constant multiple rule. So taking 4 common, and the limit of x square is c square, so we get 4 times of the c square. And here the limit of x cube at the point c is c cube. So we get the limit c cube plus 4c square minus 3. In part B, we are given a rational function, that is x power 4 plus x square minus 1 divided by x square plus 5. Now using the quotient rule, applying the limit on the x square plus x power 4 minus 1, which is in the numerator, and similarly applying the limit on the denominator, that is x square plus 5. Now applying the sum and difference rule, so applying the limit on each function separately, we get this form. Now directly applying the limit, we get c power 4 plus c square minus 1 divided by c square plus 5. Okay, in part C we will apply the property number 6, because 4x square minus 3 is inside the square root. So taking the limit x tends to minus 2 of the function 4x square minus 3 whole square the root. Now applying the difference rule, we get limit x tends to minus 2 4x square minus limit x tends to minus 2 of the constant 3. So the limit of the constant is constant, so we get 3, and here we apply the constant multiple rule, so taking 4 common and applying the limit on the function x square, we get 4 minus 2 whole square minus 3, which is equal to 16 minus 3 whole square root, which is further is equal to square the root 13. So the limit of this function as x tends to minus 2 is equal to square root 13. Now to understand the direct substitution of limits, students are advised to solve problems 21 to 28 as their homework. Here are some more exercises. Students are also requested to solve these problems from 1 to 18. If you have any issue, you can contact me on my email address given at the footnote. And finally, in references, all the materials in this lecture are provided from the Thomas Calculus, including second order differential equations, 11th edition.